notice how a bad Wi-Fi connection creates two different headaches depending on what you're doing? On a video call, your coworker freezes mid-sentence and turns into a robotic blur. But if you're downloading a file, the progress bar simply stops, waits, and eventually resumes right exactly where it left off. They're both using the exact same internet connection. Why do these two everyday applications react to a weak signal in completely opposite ways? The internet functions as a dynamic system that adapts its behavior to suit the specific requirements of the application in use. Once data navigates the global network and arrives at your home router via an IP address, a new system takes over. This is called the transport layer, and it makes the final crucial decisions about exactly how that data should be handled before your screen updates. These frustrating video glitches stem from intentional engineering choices made at the transport layer to ensure the connection remains live. Think of your IP address like the street address of a large apartment building. It gets the mail to the front door. But once a packet of data arrives, the computer still needs to know whether it belongs to your web browser or a background application. To solve this, the transport layer uses port numbers. These function as specific numerical identifiers assigned to different applications, acting like apartment numbers for your software. For example, when you request a website, that data request leaves your computer through a randomly assigned port, like 41231, but it specifically targets port 80 on the receiving server, which serves as the universal standard for web traffic. These port numbers are stamped onto the header of every single piece of data traversing the network. The moment a packet arrives, your computer reads the stamp and instantly routes it to the correct internal process. Without this numerical sorting system, the transport layer would deliver a chaotic pile of mixed data, leaving your software unable to distinguish between useful information and background noise. When an application requires 100% accuracy, like downloading a PDF or loading a bank website, the transport layer uses a protocol called TCP, or Transmission Control Protocol. TCP operates as a connection-oriented protocol, meaning that before it sends any data, it performs a formal three-way handshake with the server to guarantee both sides are ready and listening. This schematic outlines the TCP header format. Right below the source and destination ports, the protocol uses a field called the sequence number. TCP uses these numbers to track every single packet. If a packet gets dropped along the way, TCP immediately issues a backward error correction, demanding a retransmission of that missing piece. Using those very same sequence numbers, the receiving computer holds the incoming data in a buffer. It waits until all the retransmitted pieces arrive, reorders them perfectly, and only then does it allow your application to see the final file. This meticulous checking process guarantees a flawless file. However, these mandatory retransmissions create a heavy amount of data overhead, which leads to noticeable delays if your connection weakens. If TCP guarantees perfect data delivery, why choose to send data through an unreliable method? Speed often matters more than perfection. For live streaming, gaming, and real-time communication, the transport layer switches to UDP, User Datagram Protocol. UDP prioritizes speed by skipping the formal connection handshake entirely. It simply takes the data and throws it at the destination IP address as quickly as the network can handle. The protocol manages errors by simply ignoring them. If a data packet gets damaged in transit, UDP discards it. It never requests a retransmission, because pausing a live conversation to wait for a missing syllable from 3 seconds ago would disrupt the entire experience. UDP achieves the near-zero delay that human interaction requires by intentionally sacrificing pixel-perfect accuracy. The transport layer offers two distinct philosophies for handling network errors. TCP stops everything to fix the problem, while UDP keeps moving forward at all costs. A momentary pixelation or a robotic syllable indicates that the system is operating exactly as designed. That temporary glitch proves that UDP is aggressively prioritizing the immediacy of your conversation over perfect visual resolution. The modern internet relies on this invisible, constant balancing act between accuracy and speed. If you learned something new about how your network operates, hit the like button, subscribe, and tell us in the comments which protocol your favorite app relies on most.